Okay, greetings. You're almost at the end of the marathon. If you're reading this, you're getting ready for the final, midterm number 4 in week 5, same format as the others. These tests are worth half, they're worth 10% total, in line with the idea that you shouldn't have any deliverable on a course worth more than 10% of the grade in your final week. Same protocol as before, closed book, closed notes. Scratch paper provided and an equation sheet. The equation sheet will be exactly as below. No smartphones or tablets, nor smart calculators, I guess. And the tests are again in class time, Monday, Wednesday, and Friday, 8 to 8:30, but typically opening up maybe 5 minutes before that. The material we talk about is in the last really 2 weeks. The last class of pipe flow is pipe networks. External flows is week 12 and open channel flows is week 13. And the topics are picked from those. So the Monday is a question on pipe networks, 11.3. The second one on the Wednesday is external flows, and the third one is open channel flows, just going with the matching the materials on the last part of the course. So looking at flow in pipe networks, or for that matter, external flows, mainly in pipe networks. You can use the energy equation, which turns out to be Bernoulli, written between upstream and downstream, importantly, with a pump head on the left-hand side and major and minor losses on the right-hand side, the sum of them within the circuit. Pump heads are a length, as indeed are all the other terms in this equation, and it's given by the power in watts or joules per second or newton meters per second divided by the mass flow rate times gravity. Mass flow rate is also volumetric flow rate times density. The major and minor head losses are given by the Moody chart equation. You need a friction factor, a length to diameter ratio of the pipes, if it is a pipe in the network. Importantly, these are upstream and downstream and upstream velocities. This should have a square on it. These are the velocities in the pipes and the fittings. So it's important to realize that these are the velocities not at the beginning and end of the Bernoulli circuit, but in the pipes themselves. And head losses are always positive. For pipe flow, we know that we can solve class 1, 2, and 3 problems. Class 1 problems are the easiest, where you solve for head loss, where you know the volume, the velocity. The other ones are a bit more challenging. And the behavior for the friction factor, which is really an Euler number, is different in the laminar regime and the turbulent regime. Laminar it changes as a function of viscosity. In the turbulent regime, it's a function only of relative roughness and not a function of viscosity, as embodied in these two relationships here. So that's kind of preamble for the background of solving these systems. If you have a velocity, you can get a Reynolds number. If you know the Reynolds number, you can calculate a friction factor. You can use that to calculate a revised velocity, and you can go back and reiterate on that to make sure that the velocity you have is congruent with the Reynolds number and therefore the friction factor for your particular case. If you have non-circular pipe sections, then hydraulic radius is 4 times the cross-sectional area of the pipe divided by the perimeter. And the parameters that you need to use are given by the characteristic dimension, which would be the hydraulic diameter of the pipe. If you are looking at pipe networks either in parallel or series, they follow different laws. If they're in parallel, then the volumetric flow rates are additive as discharging into each of the tanks, and therefore the head losses have to be the same because they're going through the same delta Z as they go from upstream to downstream. If you wrote them as pressures going into these pipes, it would be exactly the same. These would have to be the same head losses in either case. For series arrangements, the flow through here has to satisfy that the volumetric flow rate across any section is the same. So Q1 and Q3 are the same, but the head losses are additive. They'd be smallest in the upstream wider part and largest in the downstream lower part. And for pipe networks, if you have an upstream tank and two downstream tanks, or indeed two downstream pipes, and either a single tank or two tanks downstream, then you have to solve basically for the three unknown velocities in the pipes. And typically you'd constrain that by writing that Q1 is equal to Q2 plus Q3. And that you can draw Bernoulli through each of these circuits, 1 and 2 and 1 and 3. And so that would give you three equations to solve for three values of the velocities. If this is two tanks that are downstream or upstream, it gets very difficult and you end up with a solution which is a quadratic or a cubic equation. And so typically the examples that we've done have had the same heads both upstream, at both of the outlets downstream or both of the outlets upstream. Also, you have to bear in mind that in writing the energy equation, you need to write it in the direction of flow from upstream to downstream. So if you get one of these questions, you have to write the expression in the correct mode. If you're looking at external flows, the week 12 material, we can define it by a Moody-like chart, which gives us laminar behavior and turbulent behavior. We define it in terms of a coefficient of drag or a coefficient of lift, which is defined as an Euler number. This is essentially an Euler number. And in this, you can get a force that's applied in drag, the density of the fluid, the velocity of the fluid relative to the object, and the planiform area, if for instance it's a sphere, which represents the appropriate characteristic dimension. If you divide the force by the area, this term here is essentially a pressure. So this reduces to being an Euler number with an extra half in there for the system. And so you need to know that you're on the right regime, so you need to know that you're at the right Reynolds number, again defined in terms of a characteristic dimension, maybe a diameter for a cylinder or a sphere or some characteristic dimension, which you typically be given. And from that, the appropriate Reynolds number, you can calculate where you are in Reynolds number space. You can calculate a friction factor. You can use that friction factor to be able to, coefficient of drag to be able to know this. And if you know that, then you can either solve for the force that you're applying as a function of a given velocity or a velocity that the object's moving at for a given balance of excess forces on the system. If you're solving for a free body, then you have to account for the velocity of flow past that body and the forces acting on that free body. There'd be three. There'd be a drag force, D, due to the coefficient of drag, which we've just talked about how you calculate. There'd be a weight of the body as mass times gravity. And also there'd be a buoyant force, which is the volume of the body multiplied by the unit weight of the fluid which it's displacing. And so if it was, for example, air and as the fluid and a rock as the ball, then the buoyant force would be tiny. But if it was something settling in water, you might want to accommodate for that. Just as in flow in pipes, in the laminar regime, the coefficient of drag is a function of Reynolds number. And in the turbulent regime, it's not a function of Reynolds number, but it is a function of density. And in the laminar regime, since it's a function of Reynolds number, it's also a function of viscosity in these two different regimes. So that defines exactly whether the effects are due to predominantly pressure drag, for instance, or viscous drag between these two competing regimes. So that's external flows. Open channel flows, the motive driving force is gravity, and it's due to the slope of the channel. I guess the slope of the channel really would be this, right, in this particular case. So the gradient of the channel is given by this amount, d, for the sloping top of the channel, and also which is parallel to the lower thing. Actually, this is the slope that you'd want to use. The relative slope is the drop per channel length L of the channel D. The volumetric flow rate is the average velocity of flow in the channel multiplied by the cross-sectional area of the channel. And it's also given by a strip of width 1 and depth y within the channel, which gives you the volumetric flow rate per unit width of the channel, which we call lowercase q, or an average velocity, which is just the average velocity, which is the same at every point along this channel. We can use the hydraulic radius to calculate the radius from the area of flow divided by the wetted perimeter. So the wetted perimeter is the green section on this. It doesn't include the top because the wetted perimeter only includes the part where it contacts the channel. And the Reynolds number is defined in terms of a characteristic dimension. So this would be, in this case, the area of flow divided by the perimeter. For uniform flow, we can use the Manning coefficient. This K value is equal to 1. The Manning coefficient depends on the kind of material that makes up the channel wall. This is the hydraulic radius calculated from the area divided by the perimeter. And this is the relative slope of the channel defined as the drop of the channel per length L. And so if you need to calculate the average velocity, you can always do that from this. If you need to calculate the volumetric flow rate, you just multiply that by the area of cross-sectional flow. So these are for uniform flows. Uniform flows means that the gradient, the slope of the channel surface is exactly the same as the bed. That's not the case for gradually varying flows. And so for gradually varying flows, we can define an energy, which is a function of the depth of flow, the volumetric flow per unit 1 meter section, divided by the depth and gravity. And so we can calculate the value of the energy in the system, and we can plot that against the depth of the flow in our system. For any given value of Q, we can calculate a whole series of these energy magnitudes just by systematically varying the value of Y. And you'll find that it's a term that has two roots. For a single value of energy, you actually have two values. Actually, there's another one which is negative as well, which we don't worry about. And so this means that flow, since the depth of flow is a kind of free parameter in these systems, the depth of flow can be high, in which it's flowing subcritically, or it can be low and it's flowing supercritically. Physically, what that means is if it's subcritically, then the Froude number is less than 1. If it's supercritically, then the Froude number is greater than 1, as you see here. And in the physical sense, what it means is that if it's flowing at the critical velocity, the flow velocity is actually equal to the wave speed, the celerity wave speed. So if this term is 1, and you put a drop of water and look at the ripples, they'll all radiate concentrically from that system. If it's subcritical flow, if you put a drop in, then always the center of that droplet will be contained within the concentric circles, except they won't be concentric circles because flow is dragging it downstream. Conversely, for supercritical flow, then if you put in multiple drops, the drop you put in 3 seconds ago, 2 seconds ago, 1 second ago, and now will be separated because the flow of the velocity of flow is actually faster than the celerity wave. So they'll physically look different. Because of this energy equation, you can get two magnitudes of the flow depth. And so if you are given, for instance, a volumetric flow rate, so this curve here would be for a specific value of Q, defined in this expression here, and all the terms on this are flowing at that same volumetric flow rate per unit width of the section, but at different depths. So this would be flowing at a deep depth but slowly, and this would be flowing at a shallow depth but much faster, so that the volumetric flow within the section is identical on these 2 points, and indeed on everywhere you see this. And so if you constrain the flow to be at a particular depth, either unconstrained, which would be this, or constrained maybe by an undershot sluice, then the flow here would have to be flowing at this particular point. It could choose any of these, but the geometry of flow might constrain it to be in one particular one. If you wanted to move as you go downstream from this point to this point, and that you have the same flow rate, then you physically have to move through this nose. And so you have to put a constriction in here that will allow you to get through at this particular magnitude at a Froude number equal 1. And so that allows you to look at gradually varying flows. So that's pretty much the material, everything that you should need on the test. I think we've covered here. So great luck on the test. Hope for a great result for you. And it's been great seeing you in class, or not seeing you in class, as the case may be. And again, good luck in week 15 and have a great break. Thanks so much. Bye-bye.